Hi, today we are going to discuss one more type of test called chi-square test. So in previous videos we discussed different types of test, mainly t-test, uh, dependent t-test or pair t-test. Then we have seen f-test and ANOVA test, analysis of variance test. Okay, so today our topic is chi-square test. Okay, and as we know that there are large number of varieties of tests are available to analyze a given set of data. Okay, so how we will choose the best fit method, how we can choose, uh, how we can understand whether we have to use F test, T test or chi-square test or Z test. Okay, so the selection of an appropriate method of statistical test is depends upon four different criteria. The first one is, what is the scale of the measurement? What is the scale of the measurement? What type of variable you are dealing with? Whether your variable is nominal scale, ratio scale, interval scale or ordinal scale. This is what we call scale of measurement. Okay, so we have different set of statistical analysis for ratio scale variable and nominal scale variable, so that we have to understand what type of variable we have going to deal with. Okay, and the next one is whether our sample is dependent sample or independent sample. Suppose we are having two different samples, is there is any relationship between these two samples? Okay, if there is a relationship, then that will be dependent sample. If both are independent sample, then that's known as independent samples. Okay, the third thing, what is the size of the population? What is the approximate size of the population? It is basically whether it's a small population or a large population, or small sample or large sample. Okay, and what is the shape of your distribution? Whether your distribution is normally distributed or skewed to right or skewed to left. Okay, so what is the shape of your distributions? Okay, so all these four things we have to understand before we go. All these things we have to check all these four things before we determine which one is the appropriate test. Okay, so all such kind of tests generally can be categorized into parametric test and non-parametric test. Broadly, all the tests exist in this world can be differentiated or categorized into parametric test and a non-parametric test. Okay, so how we can make this, how we are making this kind of a distinction? This kind of a distinction is mainly based on two concepts or two criteria. The one is what is the scaling of the data and what you are assuming about the sample distributions. Okay, so we can make a clear distinction between this parametric and non-parametric based on two criteria. First one, what is your scale of variable? What is your assumption about the sampling distributions? Clear? Okay. And so far we have studied Z test, T test and F test. Okay, and all these tests are applicable only for a ratio scale format or ratio scale data. What does the ratio scale mean? Ratio scale are purely quantitative variables. Okay, so Z test, T test and F test can be used only when the data are the variable are ratio scale variable. Okay, and hypothesis testing of a specified parameter. When we are doing hypothesis testing of a specified parameter means what? Specified parameter means mean, variance, proportions. So if we are doing a hypothesis testing about a specified parameter or specific parameters such as mean value or mu, standard deviation, proportions, then also we have to use z-test, t-test or f-test. Okay, then assumptions of normality, standard deviation of samples or population is known or unknown. Okay, so in all these four cases, if all these four conditions are met, then we can use certain tests that we have already seen, such as z-test, t-test and f-test. Okay, so you have to understand one thing, that z-test, t-test and f-test are applicable only for quantitative data. Okay, then if you want to learn or if you want to test a hypothesis about a specific population parameter, and if the assumptions of normality is held, that means if your population is normal and whether you know your standard deviation of your population or not. Okay, so in all such cases we can go for the test that we have already discussed. Okay, but in certain other circumstances or certain other cases, these assumptions may not always hold. So what we have to do? Suppose if the data is not qualitative, not quantitative, it is qualitative. Okay, then we don't want to find. We don't want to look at a specific parameter. Instead of, we want to do certain other things. And if the assumptions of normality is not holding, that means the population is not normal. Okay, so in such cases what we have to do, we can rely on certain other tests that do not assume any of the things that we have discussed so far. Okay, so there are certain tests we have to look into, such kind of a test. What is the peculiar feature of this test? This test won't assume anything. This test won't assume that your variable should be quantitative. Okay, or the population should be normal, or you should know your standard deviation or population standard deviation or standard deviations. This kind of assumption won't assume this kind of test. Okay, so that's why this type of test is known as distribution free test or non-parametric test. Okay, because this test will not assume anything. It is free from the assumption and free from the distribution. That's why it is known as distribution free test or non-parametric test. Okay, so these tests do not take into account any parameter free, non-parametric. Okay, and it is deal with only categorical data or what we call qualitative data, and normality assumption is not needed. Okay, so this type of a test is known as non-parametric test. Clear? Yes. Now when we come to this chi-square test, as you know that this chi-square test is a non-parametric test or distribution free test. Okay, it is a distribution free test. And when we look at this test was developed by Carl Pearson. Okay, this test was developed by Carl Pearson. Okay, in 19th century, or in exactly 19,000. In 19,000 he developed, after a long years of effort, he has developed this kind of a test to do certain things in biological statistics, or what we call medical statistics. Okay, so when we look at the characteristics of this chi-square distributions, we can see that this chi-square distribution is having only one parameter. Okay, so this parameter is known as degrees of freedom. Okay, so what is the parameter of the chi-square test? It is the df, or degrees of freedom, and the shape of the chi-square distribution depends on number of degrees of freedom, and it is always skewed to right when the sample is small and becomes symmetric if the sample is large. Okay, so you have to understand that the chi-square should not be always skewed to right, but it is skewed to right when the sample is small, and if the sample is becoming large, then this chi-square distribution will be approximate into the normal distribution. Or when the sample is large, then the chi-square distribution will be symmetric. Okay, so chi-square is a non-parametric test or distribution free test. It won't assume anything about the population. It won't assume anything about the population parameter. Okay, it is deal with categorical data or qualitative data. Okay, then it has only one characteristic called degrees of freedom, or one parameter called degrees of freedom, and the shape of this chi-square distribution depends upon this degrees of freedom. And if the data is small, then it will be a right tail test, and if the sample is very large, then it will be a symmetric test. Okay, then the chi-square test always assume non-negative values. Okay, and so that's why we usually say that it is a what we call it is a right tail test, or a skew to right. This is because chi-square is assuming only non-negative values, because we are dealing with categorical data, not the quantitative data. If we are dealing with quantitative data, then only with the 0 or negative will assume, no negative will appear. Okay, so since we are dealing with categorical data, then there is no issue of the negative values. Okay, yes. Then the average value of chi-square test, or the mean value or mean of the chi-square test, is the degrees of freedom, and standard deviation of the chi-square test is root 2 into degrees of freedom. Clear? And what is the degrees of freedom? The degrees of freedom that we have discussed in t-test was n-1 or n-2. Okay, but in chi-square test is having different varieties of use, and in each and different uses, the chi-square test is assuming different degrees of freedom. Clear? Yes. Then for what purpose we can use this chi-square test? Chi-square test can be used mainly for three purposes. Okay, the first one, to test the hypothesis of an experiment with more than two categories. To test an hypothesis with more than two categories. Okay, so this type of a test is known as goodness of fit of the test, or goodness of fit. Okay, in this there will be more than two categories of qualitative data. Okay, then the second use is to test a hypothesis about contingency table or independence or homogeneity, whether if we are having two different types of things, whether these two things are independent or dependent is. Okay, and this test is known as independent test or homogeneity test. Okay, and the third thing is to test the hypothesis about population variance. Okay, to test the hypothesis about the population variance. Okay, so for all these three different purposes, we can rely on chi-square distribution. Clear? Yes. Now we can discuss each of these tests in detail. Okay, so first we can go with what is this goodness of fit test using chi-square. Okay, so as I told you before, goodness of fit test is this test is to test an experiment with more than two categories. So that you have to remember. Okay, the goodness of fit test should be applicable for those variables that we can classify or categorize into different categories, and should be more than two categories. Okay, yes. Then we discussed binomial experiment earlier times. So here let me tell you what is the multinomial experiment. Okay, so an experiment with more than two possible outcome. Okay, an experiment with more than two possible outcome is called a multinomial experiment. Okay, so this goodness of fit test is always deals with multinomial experiment. Okay, and before we go into before we moving to further, let me discuss two concepts. The first one is observed frequencies and expected frequency. Okay, so here what is mean by observed frequency? The frequencies obtained from the performance of an experiment is called observed frequency. After doing certain experiment, okay, then we will get some frequency. That frequency is known as observed frequencies. Okay, whereas the expected frequency is n into p, where n is the sample size, p is the probability that an element belongs to a particular category. Okay, so E is nothing but n into p. N is the sample size and p is the probability that an element belongs to a particular category. That we will discuss, don't worry about it. Okay, then what is the degrees of freedom here? Degrees of freedom here, or degrees of freedom in goodness of fit test, is df is equal to k minus 1, where k is the number of possible categories. It is not n minus 1, but here it is k minus 1. Okay, so degrees of freedom for goodness of fit test in chi-square distribution is k minus 1, where k is equal to total number of categories. Okay, so what we discussed, what is the observed frequency, what is expected frequency, and what is the degrees of freedom for the chi-square test. Okay, yes. Now, in order to make you understand more about what is this observed frequency, what is expected frequencies, let me to take an example. Okay, so a bank has installed an ATM, and the manager of this bank wants to investigate the percentage of the transaction made through this ATM in same for each working days, whether the number of transactions happening in this bank is same for all days, or if there is any different or not. Okay, so for this purpose they took a 5 different days, or 5 randomly selected 5 days of data. Using this data and one level of significance, can we reject the null hypothesis that the proportion of people who use this ATM in all these days are same or not? Okay, so what is this problem actually? This problem is nothing but a categorical problem or a qualitative problem. Okay, the problem is a bank has installed an ATM, and the manager wants to know in all days this ATM has used by its customers on a same level, or is there any different or not. Okay, so for that purpose we are having the data from Monday to Friday. Monday 253 people were used, Tuesday 197, Wednesday 204, Thursday 259, and Friday 262. Okay, So from the table itself we can see that there are differences. Okay, yes. So the first step in our hypothesis testing is to specify the null and alternative hypothesis. Okay, so what's the null here? The number of people who are using this ATM is the same for all 5 days of this weeks. Okay, in all these 5 days, the total number of people who are using this ATM is almost one and same. Okay, whereas the alternative hypothesis is the number of people who are using this ATM is not the same in all 5 days of the week. Okay, so how we can specify our null hypothesis? H0 is equal to P1 is equal to P2 is equal to P3 is equal to P4 is equal to P5. Okay, which is equal to 0.20. What this 0.20 means? What? We are having 5 different days. Okay, so in each days the proportion should be 0.2 because 1 day divided by 5. Okay, second day divided by 5, third day divided by 5, fourth day divided by 5, fifth day divided by 5. So it will be 1 by 5, 1 by 5, 1 by 5, 1 by 5, 1 by 5. That's why we are getting proportion of 0.2 in a day. Okay, then what is our alternate hypothesis? At least one of these 5 proportions are not equal to, at least one of these proportions are not is equal to 0.2. That would be our alternative hypothesis. Clear? Yes. Then the third steps. What type of test we have to use? As you know that here we are going to compare the data in different categories or different days. Okay, the day is a qualitative variable, so we have to use rely on chi-square test. Okay, then the next thing, we have to determine the rejection and non-rejection region. Okay, for that what we have to need? We need to have degrees of freedoms. Okay, degrees of freedom is nothing but k minus 1. K means what? K means total number of categories. So k minus 1 means it will be equal to 4. The degrees of freedom is equal to 4. Okay, so what we have to do the next? Next you go to the chi-square table. Okay, from the chi-square table you find out a critical value for df is equal to 4 and level of significance is 0.01, because in the question we assume that we want to have a 1% level of significance. Okay, so it would be 0.01. Okay, so when we look at the table value for this, we got it is 13.277, degrees of freedom 4 and the level of significance is 0.01. Then the table value for a chi-square test would be 13.277. Okay, then what we can do? We can draw a curve. Then we can fix the critical regions, acceptance region, rejection regions. Okay, so look at this graph. As you know, it is a right tail test, a rightly skewed curve. Okay, then in this curve we are having only one tail. Okay, so there will be only one critical point. Okay, so it is 13.277. Rest of the part will be so rest of the critical rejection region, and inside of this 0 to 13.277 will be the acceptance regions. Okay, So the acceptance region is 0.13.277 and the rejection region is beyond 13.277. If we got a value beyond this 13.277 something, then we have to reject the null hypothesis, and if it is include or if it is below this 13.277 or equal to 13.277, then we have to accept our null hypothesis. Okay, then next what we have to do, we have to find out the actual test statistic value or chi-square value. Okay, so how to find out the chi-square value, that we have to take care of, that we have to understand. Okay, so look at the table. In the first column I am giving you the category Monday, Tuesday up to Friday. Okay, then we have recorded the frequencies of the visit, that's called observed frequencies: 253, 197, 204, 279, 267, and there are the total number of users is 1200. Okay, then we have to find out the P. P means what? Probability. Okay, so the probability means what here? Number of element or number of a category divided by total category. A category divided by total category. Okay, so it would be one category divided by total fifth category, 5 categories are there. So 1 divided by 5, 0.20, 0.20, 0.20, 0.20 and 0.20. Total category, total is equal to 1. Okay, then we have to find out the expected frequencies. It is nothing but observed frequency or total number of frequencies, n into p. Okay, n means what? Total number of observed frequency. It is 1200. 1200 into 0.20, it is 240, 240, 240, 240 and 240. It is called expected frequencies. Okay, that means actually in the first day, Monday, we have observed 253, but we expected only 240. We expected that only 240 people will come on a base of our probability distributions, but there were only 250. Okay, in next day also we have expected on an average 240 users, but on that day we have got only 197 users. Okay, yes, it's go on like that. Then the next one, what we have to do is we have to subtract expected frequency from observed frequency. Observed frequency minus expected frequencies. What is the difference between observed frequency and the expected frequencies? Okay, we have got 13 minus 43 minus 36, 39 and 27. You square it. 13 square 169, 43 square 1849. Go like that. Then 1296, 1521 and 729. Okay, then we have to do what? You divide these with your expected frequency. Okay, so what you will get? In the first case you will get 1069 divided by 240, it will be 0.704. The next 7.704, 5.4, 6.3 and 3.03. What is the total value? Total value means 23.184. This is our chi-square test value, or value of our chi-square test. Okay, so how we can find out this? Look at the equation. See, summation of observed frequency minus expected frequency whole square divided by expected frequency. Okay. So we have specified the null and alternative hypothesis. We have selected the appropriate test. We have found this degrees of freedom. We specified this acceptance and rejection regions. We find out the critical value. Then we have find out the test value. Now we have to take the decision. What are the decisions? In all statistical tests, the decision should be the same, or it would be the same. If actual test value is greater than your table value, or actual test value is greater than your critical value. Okay, so here the actual value is 23.184. Our critical value was 13 point something. Okay, so what is the decision here? Here the value of the test statistics is 23.184 is greater than the critical value 13.277. Okay, so if actual value is greater than, reject the null hypothesis. Is it okay? Actual value greater than, we have to reject the null hypothesis. Yes. Okay, so we rejected that. The number of person who use this ATM is not the same for 6 days. We have to reject the null means what? The null was what? In all days, the number of ATM users were same. Okay, that we have to reject, and we have to say that the number of users in different days are different. Okay, so this is how we can do the goodness of fit test using chi-square distributions. Okay, so I am repeating once again what we have to do. Find out, prepare or construct a null and alternate hypothesis. Then select the distribution to use. We have to use chi-square test because we are going to compare different categories or different qualitative data. Okay, find out the degrees of freedom. It is nothing but k minus 1. Okay, then on the basis of this degrees of freedom and the level of significance, you find out the critical value and critical region. Then you find out your chi-square value. It is nothing but summation of the observed frequency minus expected frequency whole square divided by the expected frequencies. The last one is what? You compare your actual value with your table value. If actual value is greater than table value, then you reject the null hypothesis, or you do not reject the null hypothesis. Is it clear? Yes. Now, the next use, to test for independence or homogeneity. Okay, so what is this independence or homogeneity? In this, we are testing that whether two attributes or characteristics of the elements of a given populations are related or not related. There are two attributes. Okay, there are two qualitative data. Whether these two qualitative data are dependent or independent, related or not related. That's why it is known as test of independence. Test of independence. Okay, so the chi-square test can be used to test the independence of two qualitative attributes. Okay, but in this test, as I told you before, the degrees of freedom will be different. Here, the degrees of freedom would be r minus 1, rho minus 1, then into column minus 1. Okay, where this rho r means what? total number of rows, C means total number of columns. Okay, so what is this column and row, that we will see. Okay, then for doing these things, let me to learn this thing by doing. Okay, so let me take an example. A random sample of 300 adults were asked whether they are in favor of giving more freedom to teachers to punish the students for lacking the discipline. Okay, whether you are in favor or against in punishing the students or giving freedom to teachers for punishing the students. Okay, so can we say that two attributes, gender and opinion on the issue, are independent? Here we are collecting the data from pupil. Okay, and this may be, there may be gender differences. Some people may be male or some people may be females. Okay, and sometimes they may opine that this punishing the students is good or the punishing the students is bad, or sometimes they may not have any opinion. Okay, so here we have 5 different choices. Either the respondent may be male or she may be female. Okay, and either she may agree with your argument or in favor of your idea or against your idea, or he may not have or she may not have any opinions. Or here there are 5 possibilities. And what we have to look into, we have to look into whether these opinion and gender are dependent or independent. That means if all males are opinion that if all male are opining that or opining that punishing the student is good, and all the females are opining that punishing the student is bad, then we have to say that their opinion and their gender are dependent. Because all males are opinion that all males are opining one opinions. Okay, and all females are of the take on of some other opinions. Okay, so their gender and their ideas are related. Okay, so the gender is a qualitative attributes, opinion is also a qualitative attribute, because here we are taking yes, no or no opinion. Here also they are having qualitative attributes. Okay, so these attribute, whether these two attribute is having any relationship or not, that we are going to see in this test of independence. Okay, so here males, there are we have found the data from we have got the data from 300 people. Among these 300 people, 93 were men and they were in favor of this idea. 70 people were men but they are against this idea, and 12 also were men but they don't have any opinion. Okay, similarly there were 87 female with in favor opinion, 32 people with against opinion, and 6 female doesn't have any opinion. So there are 175 males and 152 female. Okay, then total 180 people opined that punishing the students is good, but 1 or 2 people were opined that punishing student is bad, and 80 people doesn't have any opinions. Okay, and next what we have to find out, we have to find out the expected frequencies or E. Okay, but here E is different. Okay, so look at this table. This table is known as contingency table. What is called? Contingency table. Okay, it is nothing but a table with more than two or more than two attributes. Okay, So what is this E here? E is nothing but row total into column total divided by sample size. Row total into column total divided by sample size. Okay, so in first case what will be the row total is 175, column total is 180 divided by the sample size is 93. Okay, so we have got expected frequencies as 105. Okay, so the observed frequency is 93 but the expected frequency is 105. Okay, the next we have the next we have got 59, 10.5, 75, 42.5 and 7.5. Okay, so these things are known as expected frequency. How we can find out? Raw total into column total divided by sample size. Okay, then now we are going to specify our null hypothesis and alternate hypothesis. Okay, null means what? Gender and opinion are independent. There is no relationship between an opinion and their gender. Okay, the alternative hypothesis will be the gender and opinion are dependent. Okay, so what we can do, we have got observed frequency, expected frequency. Using the same equation we can find out the chi-square value. Okay, so it would be observed frequency minus summation of the observed frequency minus expected frequency whole square divided by expected frequency. It would be 8.252. What is this 8.252? It is our test statistics value for chi-square. Okay, yes. Then after this what you can do? You can check, okay, you can check what is the degrees of freedoms. Then if you got your degrees of freedom, you specify your level of significance. Okay, then you find out a value for your level of significance and DF. You find a critical value from the table. You compare to these two values. If actual value is greater than table value, then reject the null hypothesis or you accept the null hypothesis. The remaining part will be the same. The only difference is how to find out the expected frequency. Okay? Yes. So finding the expected frequency in both tests, goodness of fit test and independent test are different. Degrees of freedom values is also different. All other things will be the same. Okay? Yes. And the third use, I am not going to discuss this test. Okay, this test is to the aim of this test is to check the population variance. Okay, so in order to check whether the population variance are equal or not equal, for this purpose also we can use chi-square test. Okay, so it's a long procedure and I don't want to confuse you, and if you want to really look into this matter, you go to any of the textbook. You can see the third use of the chi-square test is to check the population variance. Okay, so if you want you can go for that. Okay, and the equation will be different from that of the previous two. Okay, here the equation will be summation of n minus 1 into standard deviation square sample standard deviation square divided by population standard deviation square. Okay, and the only thing is that this will be different, but all other steps will be the same. Okay, now so far we have discussed almost all the classical tests in statistics. Okay, then how we can know which test we have to use? For that test, the different statistician has developed different decision trees. Okay, so let me to have a concrete idea about which test we have to use. Okay? Yes. Then the first thing is whether you want to compare your mean or whether you want to find out the relationship between two variables. Okay, look at the first thing. We have two variables or more than two variables. We want to find out whether these two variables are related or not related. What we have to do? First thing what we have to check, what types of data we are having. Whether it is nominal data or interval data or ratio scale data. Okay, so both variable are nominal scale data, then you go for chi-square test of independence. If we are two data having if we are two different variables, then these two different variables are nominal scale variable, and we want to find out whether these two nominal scale variable are associated related or not, we can go for chi-square test. Okay, then if our data are ratio scale or interval scale variables, then for finding the relationship we are having some other measures like Carl Pearson measure of correlations, regressions. Okay, and suppose if you are having a mix up, if you are having a qualitative as well as quantitative variables, that time we can go for dummy variable model or dummy variable regression model, that we will learn in the econometrics part. Okay, and the next things, if you want to compare the means, now we have to check where our aim is to compare the mean, then you have to look into what kind of mean that we want to compare. Okay, whether you want to compare a sample mean or a population means, or you want to compare two sample means. Okay, again there is a question whether your population standard deviation is known or not. If your population standard deviation is known, then go for Z test. If it is not known, then go for T test or single sample T test. Okay, so here we are having only one sample or one population. If you want to compare one sample, go for Z test. If you know the standard deviation, you go for T test if you don't know the population standard deviations. Okay, now we are having two different samples. We want to compare two means. Then you have to look into whether your samples are independent or not. Okay, or whether your samples are paired or not, or your samples are dependent or not. Okay, if your samples are dependent, then you have to go for paired T test, and if your samples are independent, then you have to go for T test. Clear? Yes. Now, if you want to compare the variance, okay, what you have to do? Go for F test. Okay, and now you want to compare mean of more than two variables. Go for ANOVA test. Okay, and now you want to check the goodness of fit of the model. Go for chi-square test. You want to check the independence dependence. Go for chi-square test. Okay, so this is the decision tree. Okay, and let me to discuss one more thing, the distinction between the parametric and non-parametric test. Okay, when we look at the distinctions, as I told you before, the distinction lies in three different concepts. First one, what you assume about the population. Okay, then what is the whether you are going to whether you are going to find out the mean, variance or proportion or not. Okay, and whether your data is ordinal scale or whether your data is nominal scale or ratio scale. Okay, so in parametric test we will make some assumption about populations, whereas in non-parametric test we are not assuming anything about the populations. Okay, and in parametric we use certain normal probability distributions or some distribution like TF or TF or Z, whereas in the non-parametric test it is a distribution free test. There is no any particular distributions. Okay, and in parameter there will be some parameter like mean, variance or proportion, but in non-parameter there is no in such of parametrics or parameters. Okay, then in parameter they are using mean value as the central tendency, but whereas in non-parametric test they are using median as the central tendency. Okay, that means whenever when we use the parameter test we use the term mean. Okay, in that time mean means what? Arithmetic average or mean value. But when we discuss about the non-parametric test, we usually say that mean or average. It doesn't mean that it is arithmetic average, but it is a median average. Okay, then in parametric test we have to know certain things about the populations, or we need to have a idea about the population, whether we know the standard deviation or not. Okay, but in non-parametric test we don't need to we don't need to have any idea about the populations or the shape of the population and all. Okay, so this is the fundamental difference between parametric and non-parametric test. Clear? Yes. Now let me to discuss some of the non-parametric test. I'm just giving some idea about it. If you want to get more idea, you go for referring in a textbook. Okay, how to do that procedure and all. Okay, then the first type of test is the sign test. Okay, so the sign test is used to make a hypothesis testing about a single mean or median of a pair difference for two dependent population. Okay, so earlier in Z and T what we have done, we have hypothesized about the population mean. Okay, suppose if you are hypothesizing about the population median, then we have to use sign test, or mean of the pair differences we use T test. But if you want to use median of the paired differences, then we have to use the sign test. And why we are calling it as a sign test? Because in sign test we are using only plus or minus sign. Okay, and I'm not going to discuss its procedure. Its procedure is very simple. Okay, and if you want to learn it, go for Prem Introductory Statistics book, or you can go for referring Sharma's statistics book. Okay, Statistics for Business and Economics, J.K. Sharma, published by Pearson. Okay, the second type of test is Mann-Whitney U test. Okay, and this test is used the non-parametric equivalent of the two sample T test. Okay, so this test is only used as a non-parametric counterpart of the two sample T test. Okay, and it is used to check the equality of two population when the sample is small. Okay, so in this test we are comparing the median of two different samples, not the mean. That's only difference. Okay, so we have used two sample T test, no independent T test. Okay, so Mann-Whitney U-test is just a counterpart of its, or just a non-parametric counterpart. It is used when we have to compare two population median when the sample is small. Okay, then the third type of test is the Wilcoxon sign rank test. This is for two dependent samples. If our samples are, if there are two samples and these two samples are dependent, then instead of instead of using paired t-test, we can go for Wilcoxon signed rank test. Okay, so it is a counterpart for, it's a clear counterpart of the paired t-test. Okay, here also we are comparing the median, not the mean. Then Kruskal-Wallis test. It is just a non-parametric counterpart of ANOVA F test. Okay, so one of the major advantage of this test is that the ANOVA test is based on 3 assumptions. Okay, but this Kruskal-Wallis test will not assume anything about the population parameters. Okay, yes, but this Kruskal-Wallis test is based on only one assumption. That assumption is all population under consideration have a identical shape but differ only in location, which is measured by medians. Okay, thus the population may have different shapes or different shapes, but the assumption is that if you are comparing 5 samples, okay, all these 5 samples should have the uniform shapes. It may have any shapes, but it should be uniform. Okay, and the sample must be at least 5. Okay, and this will be used by this Kruskal-Wallis test is used chi-square distributions, and it is always a right tail test. Clear? Yes. So we have discussed 4 tests: sign test, Mann-Whitney U test, Wilcoxon sign test, and Mann-Whitney U test. Clear? Yes. Now we can compare the parametric and non-parametric test. Okay, so in parametric we are having t-test and z-test. Okay, on its non-parametric counterpart we are having sign test and Wilcoxon test. Okay, and the main feature of this test is that the test on the median for data from a non-symmetric distributions, and Wilcoxon test is the test of a median for a data from a symmetric distributions. The only difference is that sample Wilcoxon test is applicable only to compare the median of a symmetric distributions. If the distribution is symmetric, then we use the sample Wilcoxon test. But if it is not symmetric, then we can use sample sign test. Both are the counterpart of t-test or z-test. Okay, then 2-sample t-test. Okay, where we have used pair t-test. So here we are having, on non-parametric part we are having Mann-Whitney test. Okay, then on the one side, on the parametric side we are having ANOVA, one-way ANOVA. On non-parametric side we are having Kruskal-Wallis test. Okay, then one more test is there that is called mood median test. Okay, it is used to test the equality of medians from 2 or more population more robust to outliers than the Kruskal-Wallis test. Both tests will give you the same result, but this mood median test is robust to outliers. That means if we have 2 extreme values, okay, if we have extremes or outliers in our data, then this mood median test will be performed better than this Kruskal-Wallis test. Okay, then we have 2 or multiple way ANOVA test, or multiple ANOVA test, or two-way ANOVA test. Okay, So as its counterpart, we are having Friedman test. Okay, so in both parametric and non-parametric test, we are having different types of tests for the same purpose. Okay, but parametric is based on certain assumptions. Non-parametric is, it will not assume anything about, or it won't assume anything. That's the only the differences. Okay, so that's all about today's video. Okay, so in this day or in this video we discussed chi-square test. Okay, chi-square is a non-parametric test. Why it is non-parametric? Why all other tests are parametric? Uses, 3 uses we discussed. Then we used the distinction between parametric and non-parametric. Then we discussed certain non-parametric test. Then we have find the decision tree in parametric test, and we have compared the parametric and non-parametric test. Okay, so I hope that this video is helpful for you to understand all these tests. Okay, and all these tests are very simple. Okay, if you are ready to read certain simple books, and if you are ready to do certain if you want to work out on this, take some simple problem from textbook, then you practice it, then you will learn it. Okay, the theoretical part of this chi-square test I am not discussed. If you want to look into that, okay, it is highly mathematical, how the Pearson got this chi-square and all. Okay, and its relationship between z and all that, all you can, if you want to understand, then go for S.C. Gupta's textbook statistics. Okay, in that they are given everything about its derivation and all, but I am not using the derivation. I am just giving you for what purpose and how we can use this chi-square test. Okay, so we almost done the statistics. Okay, now only one part is left with us, that is the correlations. Okay, so in the next video we will come with a correlation, regression, and some part of the index number if you want, but the index number is not there in the syllabus. Okay, so we will see you in the next video. Thank you.